We'll talk more about the three laws of motion, but I just thought you might take some notes here. So the first one is that an object at rest will remain at rest. An object in motion will remain in motion at a constant speed in a straight line unless acted upon by an outside force. So the notion of this is that, if you take a baseball and throw it into space and there's no outside force acting on it, this thing is going to travel at a constant speed forever and ever. It doesn't take a force to keep it going. It just tends to keep going. And this is really, Newton is building on the idea that Galileo developed, which is the idea that objects have inertia. And I'll do a bunch of really lame demos in class about inertia and all of this stuff. This is the pulling the tablecloth out from under the plates, and the flowers still stand, kind of a thing, right? But just keep in mind also that if an object's moving, it tends to keep moving unless there's some outside force acting on it. The only reason your car stops moving if you turn off the engine is that there's probably some amount of friction that slows it down. And that's what Galileo was smart enough to figure that out. The second law is, and we'll talk more about this, right, is that if there is an outside force, this outside force is going to cause an acceleration. And that acceleration is the force divided by the mass, right? The more force you have, the faster the acceleration. The more mass you have, the slower the acceleration, basically, is that concept. And then the last of Newton's laws of motion is that for every action, there's an equal and opposite reaction. An example of this is, and I will do some demos of this, right? But an example of this is, if you have a rocket, of course, the rocket is shooting gases this way, right? And the gases push the rocket this way. Or if you throw a baseball, the baseball goes this way, but the baseball pushes on your hand this way. For every action, there's an equal and opposite one, right? So anyway, I've got some demonstrations. Let's look at the second law and double click on this thing, right? Kilogram, for mass, there's not much to it. We're going to use a kilogram, and 1 kilogram is, of course, kilo just means 1,000, right? So it's 1,000 grams. So in chemistry, you use grams. In physics, we use kilograms. And as I make this video, we're on the verge of creating some conceptual definition of kilograms, which is kind of exciting. And then the acceleration is, of course, meters per second squared. And we can get this from using x, vi, vf, a, and t, right? So that makes this, these problems a little harder, is that we have to solve for the acceleration, right? Using our equations, our kinematic equations. And then force is of course in newtons, okay? And this is the net force, okay? This is actually the vector sum of all forces. So for example, if I've got some object here and I've got 10 newtons this way and 3 newtons that way, right? The net force in this case is 7 newtons this way, right? And we'll do stuff like this, okay? We'll do problems with that. That's how you make these problems maybe a little bit harder, a little more challenging, okay? I guess let's look at a couple examples here, okay? What force causes a 4 kilogram object to accelerate at 6 meters per second squared? Well, let's figure it out. F equals ma, right? So F is equal to 4 kilograms. And it's accelerating at 6.0 meters per second squared. And that equals 24 kilogram meters per second squared, or 24 newtons. There you go. Right? That unit in N is equal to newtons. Okay? So that's our base unit. It's made out of kilograms, meters per second squared, because it's MA. Let's look at the next one. The next one's, of course, a somewhat more difficult problem. Right? A 2.1 hammer accelerates from rest under the influence of a net force of 120 newtons. What is its final velocity if this force is exerted over a distance of 78 centimeters? Okay, so step one, basically it's two different problems, right? Step one is let's use F equals ma and find the acceleration, right? So 120 is 2.1 times a. And this is newtons, and that's kilograms, and then we're trying to find acceleration, right? So let's see, 120 divided by 2.1. Dyslexics beware. This acceleration is 57.14 meters per second squared. And the units come out, right? Remember, a newton is a kilogram meter per second squared, and then we just divide it by kilograms. Notice that we end up with meters per second squared, which is, you know, what the way it should be, right? But now we've got to solve one of these guys, right? But this isn't hard. Let's see. Let's assume it started from rest. They don't really say. Let's say 0.78, they being me. All right, and then our acceleration is our 57.14 meters per second squared. I guess we should put units on these things, right? We want to know the final velocity, so I'm going to use no t. Okay, so let's see. Final velocity is 0 squared plus 2 times 57.14 times 0.78. Oh, the reason this is 0.78 is that that's centimeters, right? So you got to divide by 100. That's what's going on there. Okay, let's see. Square root of 2 times the answer I just got times. So I just did up arrow there, 0.78. And I get that the final velocity, the absolute value of the final velocity is 9.44 meters per second. I can't think of a reason why this would be negative. So I'm just going to say it's 9.44 meters per second. Ta-da. So in these problems, some of them are do F equals ma, then do that first, then do this second. Okay, I'll give you this clue. If you know the force and the mass, you're going to do this first. Okay, if you don't know the force and the mass, then you're going to do this first. You're going to solve for the F equals ma first. Okay, and there's two different types, and we'll practice those in class. Okay.